Okay, welcome back, Physics 20s, to our next lesson in Chapter 8. Now we're going to be looking at open pipes. Last time we were looking at closed, which was one end open and one end closed. Now we're going to be looking at open pipes where both ends are going to be open. But just before we go into that, I wanted to bring up some terminology that I might have missed in previous sections. When we were talking about interference, if we have a wave on this side of a string and a wave on this side of a string, and they're coming together, we talked about that when they meet in the middle, their amplitudes are going to be added together. So say this was something like 4 centimeters and this was something like 4 centimeters. When they add together, they're going to be 8 centimeters. The word for this is called a constructive interference, when they add up and they're making a larger wave when they meet than they were when they were on their own. Now the opposite of this is if we have a wave on the bottom like this and a wave on the top like this. Let's say if this is like 3 centimeters and this is 4, and they meet in the middle, there's just going to be 1 at the top. There's their amplitudes come together. This one would be -3 because it's on the bottom. This would be plus 4 because it's on the top, and we get a +1 when they add together. They're still adding together, but because we have the amplitude has gone down, this is called destructive interference. So make sure that you know those terms for the test at the end of this chapter and at the end of this unit. But today we're going to be focusing on looking at pipes. Now recall this was from before when we were looking at closed pipes. There was a closed end over here and there's an open end over here. And we're talking about how much of a wavelength would fit in. There had to be a node here and an antinode at the open part for all of these closed pipes. And we talked about the different parts or fractions of a wavelength that could fit inside. So the fundamental frequency was when you fit 1/4 of a wavelength was equal to the length of the pipe. The next one was when we had 3/4 of a wavelength was the length of the pipe. And the next one we saw was 5/4 of a wavelength is the length of the pipe. This was called the fundamental frequency. Fundamental, and then it was multiples of that, which was harmonics. So going here to the next one is 3 times bigger than the fundamental, so this was the third harmonic, and then going to here is 5 times bigger than the fundamental. This is the fifth harmonic. All right, so it's multiples of that. The second harmonic and the fourth don't work because that would leave a node here if we were only getting to half of a wavelength, or if we were getting to 1 full wavelength, that wouldn't work to have a node there. So 1, 3, and 5, then 7, 9, and keep going up like that. But now we're going to look at open pipes that are open at both ends. So just like we saw from before, there needs to be an antinode at this open end, and there also needs to be an antinode at this end. So there's not a node there because it's not closed like we saw in the closed pipe. So now we need to go from antinode to antinode. And if we remember this diagram from before, we have a wave and then it reflects and comes back. And this is how it interferes with itself and resonates. And there's equilibrium. Places like this where we have a peak and a trough were called antinodes. And places in the middle where there'd be no movement. If you were shaking like a string or a spring like this, it wouldn't be moving in the middle. Those were nodes. So now instead of looking at node to antinode, we're going to be looking from antinode to antinode. Okay, so let's say we were starting right here. How much of a wave would fit into an open pipe? Well, before we went antinode to a node, now antinode to antinode. Our next one, if we're traveling in this direction, would be right here. This would fit inside of a pipe. So say this orange color represents the length of a pipe. If a pipe was that big, that much of the wavelength would resonate because there's an antinode at both ends. All right. You could make the pipe longer and go to the next antinode, which would be right here in line with that. And that would resonate as well, and that would be moving up a harmonic. So let's take a look at that with a different diagram that I've prepared. We have 3 different pipes here. I'm going to be trying to fit those wavelengths from antinode to antinode in each one. So the first one where we fit antinode to antinode, all right, this is the shortest section like I showed in the last slide. This is how much of a wavelength is what we're going to look at now. Well, if it goes up and down, if we see the green one goes up and down, that's half of a wavelength. Same for the red, it goes same for the yellow, it goes down to up. So half of a wavelength there is fitting in there, antinode to antinode. So I'm going to write off the side here, half of a wavelength is equal to the length of that pipe. Now, what if we go up to the next one? I compressed that diagram there. So we go antinode, antinode, that's what we saw in the first one, but now we're gonna stretch it out to the next antinode. Well, how much of a wavelength is that? When we go down, up, down, that's one full cycle of the wave. Same with the green, up, up, one full cycle. So this is one wavelength or 2 halves. I'm gonna write it as, I'm gonna write it as 2 halves because that shows how much it is of the first harmonic. We just doubled that from 1/2 to 2 halves of the wavelength is equal to the length of the pipe. If I go up to my next one, I've compressed it even more. We have antinode. This was the first diagram there, second diagram here, and the third one hits this antinode. How much of a wavelength is that? Well, we go down, up, there's 1, and then another half. Same thing for the yellow. Up, down, there's 1, and another half. How many halves is this? It's a full one and then 1 extra. So 3 halves of a wavelength is in the length of the pipe. So what we can see here is we keep going up by half of a wavelength as we go to the next frequency that is going to resonate. So this one at the start, the first one that's going to resonate is the fundamental frequency. The next one is going to be our next harmonic. Now, the last time we said the third harmonic because it was 3/4 compared to 1/4. This is going to be called the second harmonic because we had 1/2 and now we're at 2 halves. So it's a multiple of 2. This one, 3 halves, is going to be our third harmonic. So we see with an open pipe, it doesn't have to go 1, 3, 5, 7. It shows 1, 1, 2, 3, 4, and it keeps going up as multiples of that half. So again, just going to emphasize this is the first harmonic or the fundamental frequency. The next one here for number 2 was our second harmonic. And that's where 1 full wavelength is in the length of the pipe, or 2 halves. And this is our third harmonic. We could keep going up to 4th harmonic would be 4 halves or 2. 5th harmonic would be 5 halves or 2.5, and keep going up in that way. And so the questions are going to be pretty much identical. Now you just need to know that it's going in terms of halves instead of quarters. So let's look at this question that says, what is the fundamental frequency of an open pipe that is 50 centimeters long and the speed of sound is 343? So let's start with a open pipe, and it's asking for the frequency. So we're going to use the universal wave equation, V is equal to lambda F. We're asked for frequency, so we're going to find that by dividing by wavelength. So we need velocity divided by wavelength will give us frequency. We know velocity is 343, so now we just need to find the wavelength. Let's draw the wavelength that's in this pipe here. It says the fundamental frequency of an open pipe. So we know it goes from antinode to antinode in an open pipe, and the fundamental is the antinode to the very next antinode. It's the longest wavelength that's going to fit in there. So we go from here down there, here, up there, and we know that this is half of a wavelength. So from this we know half of a wavelength is equal to the length of the pipe. So now we can use that length of the pipe to figure out the wavelength. How do we rearrange this for wavelength? Well, to get rid of half, we're going to times by 2 and times by 2 on this side. So wavelength is equal to 2 lengths of the pipe. Wavelength is equal to 2 times 50 centimeters, so 0.5 meters, and the wavelength is equal to 1 meter, kind of a nice number. We'll plug that back over here for the green, and we go velocity of 343 meters per second, divided by a wavelength of 1.0 meters, gives us a frequency of 343 hertz. So very similar to the last examples, just using different ratios here compared to the length and the wavelength. Just do one other example here, kind of going the other way, where it tells you the frequency of to find the length of the pipe. So this one says the second harmonic of an open pipe is 650 hertz. How long is the pipe? Speed of sound, again, 343. So I'm going to start again with the universal wave equation of V is equal to wavelength times frequency. What's going to tell me the length of the pipe is figuring out what the wavelength is. So I'm going to divide by frequency on both sides, and we've been given the velocity of 343 and the frequency of 650 hertz. So that's good. And we can figure out what the wavelength is going to be. And I'm getting a number of 0.5277, and that's in meters. Now again, that's not what it asked for. It didn't ask for wavelength, it asked for how long the pipe is. But we're going to see that those are very closely related here because it says the second harmonic of an open pipe resonates at this. So let's first draw what the second harmonic would look like. So we know it has to go antinode to antinode, but it's not going to be antinode to the next antinode or the first one that comes up. We're going to skip over one and go to the second one. So it's going to have an antinode in the middle as well. So it's going to go like this, like we saw at the diagram before from the second harmonic. Well, how much of a wavelength is this? Well, it goes down, up, and then back to the top, which completes one full cycle. And as we saw from before, 2/2 of a wavelength is equal to the length of the pipe for the second harmonic. 2/2 is the same as 1, so the wavelength is equal to the length of the pipe. So actually for this question, we don't have to change this number at all. We just keep that number as is, probably round to significant digits, which it looks like there's 3. So 0.528 is our answer in meters for the length of that pipe. So that'd be 52.8 centimeters. Now you might be thinking, well, what if it isn't that easy? What if it's not just one wavelength? What if we have something like the third harmonic? And it's not too much more difficult there. I'll just show it in orange. If it was the third harmonic, we'd say, well, that's 3/2 of a wavelength is equal to the length of the pipe. How we'd solve for the length of the pipe, given that we know the wavelength here, is we just have to multiply that number by 3/2. So we go 3 over 2 times our wavelength, which we already found, 0.5277 meters. So you just multiply by that fraction based off the harmonic. So that's it. Not much new, just looking at different ratios or different fractions that fit in an open pipe compared to a closed. But that's all you've got for today. So give those practice questions a try, and I will see you in the next lesson.